Thanks.
Yeah, okay. Hello, everyone. Welcome to the Crunch seminar this week. And today, as usual, we have two speakers. The first speaker is Professor Hao from the School of Mathematics in Tongji University in China. So Dr. Hao is currently a professor in Tongji University, and his research interest is in the modeling and analysis of complex systems in science and engineering. He's currently working on research directions, including the advanced Markov and non-Markov modeling techniques and spectral analysis and mode detection of stochastic systems and machine learning approaches to time series analysis and some relevant application in biophysics. So today he's going to give us a talk with title Machine Learning Approaches for Thermodynamic and Kinetic Analysis of Molecular Systems. So let's welcome Professor Hao for his talk.
Okay, so yeah, let me start. Okay, so I'm sorry for due to a technical problem. First of all, I would like to thank Professor Kaliniakis gave me such an opportunity to introduce my my research in the past years, in fact, on applications of machine learning approaches to the thermodynamic and the kinetic analysis of molecular systems. Okay, so just let me start. Of course, so this I think so. If you have any question on this talk, then you are welcome to just present it to me at any time. Okay, so let me just first introduce the research background. Okay, so my research focus is in fact comes from the molecular dynamics. Okay, roughly speaking, molecular dynamics is a specific computer simulation technique. It was used to simulate the movements of atoms and molecules of a molecular system. So, for example, here the video shows the unbinding processes between two protons. Okay. This is very important for the researcher in computational chemistry or statistical physics or the biophysics, because it can give us some description of the conformation process of some complex molecular dynamics at a atomistic level. Okay, and but the system is very high dimensional. Okay, so because for example, for such a system, then the original phase space is a very high dimensional space, because each position of each atom will be one freedom. So you can imagine that this is a process. The simulation process is really high dimensional, and so we cannot get anything useful just directly from the simulation data without any quantitative analysis. Okay, so if we want to get some physical or chemical information from the simulation data, we must perform some analysis. So generally speaking, people will care about two kinds of the analysis. One is thermodynamic analysis. So for example, if we consider a proton, the folding and unfolding process of a proton, then the thermodynamics means that we care about, for example, the stationary probability or the equilibrium probability of the folding states and the unfolding states. Okay, that is thermodynamics. And another kind of the properties is the kinetic property. So that means, again, let's consider the example of the proton folding. Then the kinetics means we care about, for example, the transition rate between the folding state and the unfolding state. From the perspective of the computational physics, the thermodynamics focus on the sampling problem. So that means we need to develop some more efficient sampling technique to explore the energy landscape. And the kinetics is the focus on the macro modeling. So we will use some modeling tools to describe the kinetics of the system. And finally, we hope to combine the two properties and get a complete description of the molecular properties. Okay, so that's the whole objective or motivation of my research. Okay, now let me first talk about something about the macro modeling. Of course, because from the perspective of the statistical physics, so the molecular motion is primarily driven by thermal fluctuations. For example, the Brownian dynamics, the Brownian motion proposed by the Einstein, right? And thus it can be considered as a stochastic and approximately Markovian system. Okay, then now the problem is that how can we describe? So we have some simulation data, and how can we describe the dynamics of the Markovian system? One of the most commonly used method is called the finite rank Markov model, or the finite rank Kuhlmann model of a Markov process. And the key idea is something like this. So suppose that we are given some simulation trajectory on the high dimensional phase space. Okay, so from x1 to xt. But xt means the state of the system at time t. For example, the positions of all the atoms. Okay, and then we try to design some mapping chi. So chi consists of a lot of observables of the states. And then we try to model a linear dynamics to describe the evolution of the state at the observable space at sometimes some low dimensional observable space chi. And so the theory underlying the finite rank linear model, in fact, is the linearity of the Kuhlmann model or the transfer operator, the Kuhlmann operator and the transfer operator of the microprocess. And because this is a linear model, then we can calculate almost everything that we are interested in from such a model. For example, we can approximate the transition density, we can approximate the test scale of the system, we can approximate the dominant components, for example, the dominant eigenfunctions of the system from this model. Okay, in fact, so such a model, it contains a lot of different models. And I think one of the most famous one is called the Markov model. It is also called the Woolen method in the field of the fluid mechanism. The idea is very simple. So yeah, for example, we are given a Markov process, we are given a trajectory data. So firstly, we try to divide the whole phase space into several discrete states. Okay, and then we ignore the kinetics within the discrete state, and we only care about the transition dynamics between the states. Then we can see that we discretize the original continuous space Markov process into a finite state Markov chain, right? And the kinetics Markov chain can be completely described by the transition probability matrix, right? So we will only need to calculate the transition probability from the trajectory data, and then we can perform all the analysis. And we can see that this is, of course, a specific case of the finite dimensional model as we described before, because we can define the chi I is just an indicator function of the i's discrete state, right? So this is a specific case of that model, but it is also it is commonly used in the field of the computational chemistry. And in fact, so in the past, I think in the past 10 years, so this is the focus of my research. And so this paper is a review paper of this field about 10 years ago. And okay, so and in this paper, I proposed a frequency an optimization algorithm for estimation of the transition probabilities with under the constraint of the time reversibility. And this is one of the most commonly used algorithm in this field, and so it is used the PyEmma. So this is a software developed by our group, and it is also used another package on the Markov model developed by the Stanford University. So yeah, it is a very common algorithm for now. Okay, so that is about the Markov model. But of course, we can ask two questions. So first question is that can we do not just use the indicator function, but use some more general functions? The answer is yes, of course. And in fact, so in the field of the fluid mechanism, people have developed such a method called the extended dynamic mode decomposition. Okay, so that means we can use some general nonlinear observables to construct the linear model. So this is a nature extension of the macro model. Another question is more important, in my opinion. It is more important and more practical in applications. So that is, generally speaking, we want to get some low-dimensional representation in the system. Then, how can we get the optimal low-dimensional state representation from the trajectory data? Okay, so that means, so if we are given the dimension of the observable D, so we are given the dimension, and how did we choose the optimal observable that can describe the whole dynamics? So this is a very important question. And yes, here I just give you some past answers. And I think one of the most important answer in physics, so that is focus on the metastable state. So for example, let's consider a one-dimensional stochastic process, and then we can see that there are 4 potential values here. So this is a figure about the transition density from state X to Y. So we can see that there are 4 metastable states here. Then this theory told us that we can, if we design the Markov state, or we perform the state discretization based on the 4 potential values, then we can get a very good Markov model. And in fact, in theory, we can further show that if the transition probabilities between the potential values is small enough, then it will be close to an ideal Markov model. I mean, finite state Markov chain. So this is the first answer, but the key advantage of this answer is that it can be only applied to the metastable states. Okay, so for example, again, for this system, so for 4 states, so if we want to get a 4-dimensional model, then the answer is clear. We just need to try to partition it into 4 states. But so if we try to get 5, so for example, if we try to get to 5 states, or 4 states, or more states, then how do we design it? So it cannot be answered with this theory. So another answer, I think it is a more thorough answer. So I think it is a very good mathematical result. So it is published in 2010. And the answer is that, so the ideal choice of the observables, it should represent the dominant eigenfunctions of the macro processes by linear combination. This is a very important conclusion because, for example, let's just say this example. So suppose that we have a diffusion process. It is driven by 2 potential values. Of course, if we try to partition the whole system into 2 states, it's very easy to choose, right? We only need to divide the system into 2 potential values with a boundary 0, and we can get a very good partition. But the question is that, so how about if we want to get 10 or 5 or 10 states, then how can we do? Based on this theory, it tells us, so if we want to get more states, then the other states, it should be choose close to the boundary, because these states will be more important to describe the kinetics than the other states. So this is a very good answer, but the key problem is that this is not a data-driven approach. Because in fact, we don't know what is the transfer operator of the system in practice. And we don't, so that means we don't know what is the exact values of the eigenfunctions. So that means we cannot truly evaluate the approximation of the dominant eigenfunctions. Okay, so in the last 3 years, we found another answer. So that is focused on the approximate error of the transfer operators. So we try. So in fact, so this idea is also very direct. So we try to find some good chi, so that the transfer operator k tau. So k tau is the transfer operator of the true macro process. And we can also define another transfer operator, so k hash tau. So this is the transfer operator defined by the model. And if, of course, the ideal choice of the chi can minimize the modeling error of the transfer operator. Right? Here we use the Hilbert-Schmidt norm to describe the error, because later we will see that it can give us a computable result. And so this is the result. Okay, so due to the limit of time, I will ignore all the details, but just show the principle. So we propose the variational approach for macro processes one. So the key conclusion is shown by this equation. So the left-hand side is just the Hilbert-Schmidt norm of the modeling error, and we can show that it can be decomposed into two parts. The first part is just the Hilbert-Schmidt norm of the transfer operator itself. It is unknown, but in fact, we don't need to know that because this is a constant and independent of the modeling. And the second part, we call it the ramp score. So this is a quantity. Sorry, I ignore the detailed definition of this score, but I can tell you that it only depends on the matrix K. Okay, so the coefficient of the transition probability matrix in the model, and the C chi 0. So this is in fact the covariance matrix of the observables chi, and the C chi tau. So in fact, this is a time lag covariance matrix of chi. Okay, so it means that based on this decomposition, we can quantitatively evaluate the approximation quality of a macro model without any intermediate model. So because if we are given a simulation trajectory, then we can directly compute the ramp score from the trajectory, right, without any other model. So because all the quantities can be directly computed from the trajectory or from the model itself. And then based on this score, we can then compare the modeling error of different finite rank models, right? And further, we can try to optimize the choice of the basis functions of the observables and obtain the optimal in some sense macro model for example, by deep learning. So for example, we can use a deep neural network to describe the observable functions and get some optimal description of the system with a low dimensional model. Okay, so this is just the structure of so we call it the VAMPNet, and the structure in fact very simple, right? So we have some xt, the system state at time t, and then we have the system xt plus tau. So in fact, if we combine them, we can get a transition pair of the system state. And then we perform the feature mapping of the observable functions to get some chi xt, and we also get some chi xt plus tau, and combine them together and calculate the ramp score. And then we try to maximize it by using the stochastic gradient descent to update all the parameters of neural networks, and that's it. Yes, and the result is very good. Yes, we for example here we try to apply it to the NTR9. So this is a kind of small protein. So we try to use such a method to investigate the folding process of this protein. And it's very interesting. So, okay, so sorry, there is a mark here. So here, in order to get some interpretable result, here we design that so the chi must be a fuzzy partition function. Okay, so that means each element of chi must be a membership function of the whole state space. Okay, and then so by using such a model, so when we choose the dimension of the observable function to be 2, we will find that so the neural network can give us a folded state and unfolded state of the protein. So here, this is called the protein contact map. Okay, so it is some map that can describe the structure of the protein. And so if we increase the number of the states into 5, then we can find that we found 2 different folded states. And we found one intermediate state, so between the fold and unfold. And we found one unfolded state, and finally we found some misfolded states. So that is about the macro modeling. And further, we also combine such a variational approach and the generating model. So in fact, something like a GAN. Okay. And so here we try to use the generating model to reconstruct the full state from the low dimensional representation. So in fact, so this is somehow conditional generative model or conditional GAN. and then we combine it with the VAMPnet. So why we do so? Because based on this one, we can find that we can find the kinetics of the system and some new configuration, some new molecular configurations simultaneously. So, for example, we do such an interesting experiment. So this is the aniline dipeptide. I think so this is a very common example used in the molecular dynamics. And it is well known that the aniline dipeptide, its conformation dynamics can be very characterized by two dihydroangles, so phi and psi. Okay, so here what we do is that we firstly perform the molecular dynamics and get some data, and then we cut some data out of the scheduled data. So for example, here we cut the data here or data here and so on. Okay, so we cut some data and we assume that these data are unknown, okay, are unavailable. And then we try to use this model, so this deep Markov-Stein model, try to learn from this data, and then we try to use the obtained model to generate some new configurations around these areas. Okay, so it will generate some new configurations around the unknown area in the reaction coordinate phase space. Okay, and then we combine the generated configurations and the true configurations obtained from the molecular dynamics, and we found that they are very similar. So that means based on this structure, it seems that the neural network can learn how to generate, a reasonable molecular configurations. Okay. And there are some recent progresses along this direction. So firstly, we also consider that how to apply the VAMPnet to perform modeling of kinetics under some physical constraints. I think one of the most important physical constraints is time reversibility. This is a very important properties for the molecular systems. And another progress is that it can be shown that the VAMP, so this variational theory, it cannot be applied to the deterministic systems. Or in practice, so for some stochastic systems, but with very small noise, it can also not work well. And so in order to solve this problem, we proposed a new kind of kernel embedding based VAMP, and it can solve the difficulties for the deterministic systems. And the last progress, it is not by us, but followed by another chemistry group in the University of Chicago. And they call it the state-free VAMPnet, and they use it to approximate the dominant eigenvalues and the eigenfunctions of the molecular systems. Okay, so that is about my just a brief introduction of my work on the macro modeling. So starting from this slide, I will talk about something about the.
How can I ask a question?
Yeah, sure.
Okay, so this is all Markovian system. This is molecular dynamics, right? But if you cross grain,
yes,
if you cross grain, and then if you cross grain, then you have inherently you have some memory because of the cross graining, like yes. Maurice Zwanzwijk suggests. And the question is, how would you modify, if you have a memory kernel, how would you modify this technique to get macro models? And if there is because you still expect that you can get actually low dimensional models from trajectories, but how do you do that for cross-grained systems which are not Markovian?
Okay, so in fact, this is another topic. Okay, so here in the previous research, our objective is that if we want to find some low-dimensional chi, so that so in fact, so we want to get some cross-graining so that it is very close to Markovian dynamics. So without memory, so that
no, that's not. I'm not asking how you find cross-grained models.
Yes.
I'm asking if the method can be applied, the VAMPnet can be applied to a cross-grain system, because cross-grain systems inherently have memory, therefore they are non-Markovian.
I see.
So So you need to do something. You need to do a correction term because you use the Markovian property to come up with this linear system and the Koopman operator.
I see. In fact, I do some research, but it is not based on the VAM. It is based on. Okay, so in fact, so we can show that it can be somehow solved by the Heidelberg model, because so that is something like this. So we firstly we assume that so for a given non-Markov process. So one assumption is that we assume that there is an underlying macro-process, right? But the problem is that we only get some observables or some coarse-graining result. Then the observables are non-Markovian. Okay, so then based on such an assumption, and if we further assume that there is some low-dimensional representation of the underlying Markov process, then we can get, so firstly, we can get some Heidelberg model, but later we found that this is not necessary. I mean, even if the underlying Markov process has some low-dimensional representation, it may not be a Heidelberg model. So we proved that, in fact, it can be described by a specific model. It's called the observable operator model. This is, in fact, an extension of the Heidelberg model. And so firstly, in theory, we show that it can be described by an OOM, so observer operator model. And we also show that we have some very efficient way. So in fact, the algorithm is much more efficient than the traditional EM algorithm of the Heidelberg model and to perform such a modeling problem. But this is somehow beyond the talk today. If you are really interested in that, then maybe we can discuss it later. And in fact, I think this is a very interesting topic.
Okay, thank you.
Okay, you're welcome. In fact, I think the observer operator model. This is a very this model has been proposed for a long time in the community of machine learning, but people don't know how to use it. So I know it is developed by the Herbert Jäger in Germany, but he don't know how to really apply it. And later we found that it is really useful in the molecular dynamics. Yeah, this is another interesting story. Anyway, so let's continue this talk about the sampling. Okay, so so now let us transfer from the Markov modeling to the exploration of the complex energy landscape. Okay, so firstly, we need to know one thing is that the molecular dynamics, it is a really expensive thing. So for example, if we want to get some molecular dynamics with just 2 milliseconds, okay, so but from some complete complex proteins, okay, then 2 millisecond MD it requires 20,000 GPU days, and the energy consuming will be about 500 gigajoule. As a comparison, so if we want to burn a Saturn V rocket, so this is the largest rocket that the human has, and deliver 50-ton payload to the lunar orbit, then the energy consuming will be 1,500 gigajoule. So yeah, so from here we can see that the molecular dynamics it is really energy consuming. Okay, and in fact it will generate a lot of carbon emissions. Okay, so then there is a very natural question is that how can we accelerate such a process? Okay, because direct MD it is really time consuming and energy consuming. And so in the past years, I think in the field of the computational chemistry, people proposed a lot of techniques, and most of them focus on the enhanced sampling. So the key idea of the enhanced sampling is we try to add some bias to the original potential and make it easier to sample. And then we try to reconstruct the unbiased landscape from the best simulations. So that is the enhanced sampling, and I think some famous algorithms include the parallel tambourine, the umbrella sampling, the metadynamics, and so on. So this is one solution, but a major difficulty of the solution is that for most of the solutions, for example, umbrella sampling and the metadynamics, we need some low dimensional. We will also need some good reaction coordinate, some low dimensional reaction coordinate In fact, this is a very strong knowledge. And in many cases, we don't have such a knowledge. And another solution is, so we also tried to combine the macro modeling that we proposed before and the in-house sampling together. The idea is something like this. So we will, so because in-house sampling, it in fact so involve the simulations under different ensembles. Okay, so for example, in parallel tempering, then we will perform a lot of MD simulations at different temperature. Okay. So here, in this method, we will use a Marcus model to describe the kinetics of each ensemble or each thermodynamical condition, the simulations in each thermodynamical condition. The key difference between the macro model here and the previous is that, so here, all the macro models, they will share the same reference distribution. Okay, so in fact, they are coupled with each other. And then we develop some algorithm that can well approximate the macro models of each ensemble and the corresponding stationary distribution, and then we can reconstruct the unbiased equilibrium distribution. So this method we call it the TRAM, or multi-ensemble macro model, and we developed a lot of different methods for different situations. And the most general one is proposed in 2016. Okay, so in this paper, we call it TRAM. And so in our own opinion, this is an important technique because it really extends the test scales of the molecular system that the MD simulation can achieve. Okay, so for example, we consider a specific, so PMI, MD, MD2, so in fact, a bonding process between a protein and the ligand. And so here we use the proposed method, so the TRAM method, we for the first time, we realize the direct estimates of the kinetics beyond the second time scales by using simulations of all atom MD model for such a system. So this is an important conclusion in the field of computational chemistry at that time. And yeah, the last solution is just proposed in the past, I think, 2 years. Okay, so that is by using the latest machine learning technique. So that is normalizing flow. Normalizing flow, maybe someone knows. Okay, so if someone don't know it very well, so I'll just give you a very brief introduction about normalizing flow. So normalizing flow is a specific kind of the deep neural network. It consists of a lot of invertible transformation units, and finally, so we can use it to how to say, we can use it to get an invertible mapping. So that means, so for a given normalizing flow, we can get the mapping from the input to output and the mapping from output to input simultaneously. Of course, here in normalizing flow, the dimension of the input and output are the same. Okay, and then based on such an invertible neural network, then we can apply it to approximate the density. Right? We can use it as a generating model. Right, so for example, in the generating model, for example, in GAN or in VE, we all know that. So the structure is that, so we will use some simple random variable as input. So for example, just some Gaussian distribution as the input, and then we hope to by using the complicated transformation defined by the deep neural network, then we will get a very complicated random variable at the output layer. Right. This is the same for the normalizing flow, but the key difference between the normalizing flow and the other generating model is that because the mapping is invertible, then if we know the probability distribution of the input, for example, if we know it is a Gaussian distribution, then we can get exactly the probability density function of the output based on this equation. Okay, we only need to calculate the determinant of the Jacobi matrix of the neural network, and then we get exactly the density of the output. And based on this one, of course, we can then use it to approximate a very complicated density, right? And in fact, so almost at the same time, okay, so in the last years, people found this is a really useful tool in statistical physics and in chemistry. So, for example, people want to use it to analyze the equilibrium distribution in the spin systems. Okay, so this is published in 2018, and people also applied it to the lattice QCD, and we applied it to analyze the equilibrium distribution of the molecular system, and we call it the Boltzmann Generator. In fact, the structures of all the nonlinear flow models are similar, but there are some detailed difference. And here we only focus our own work. Okay, so the Boltzmann generator, in Boltzmann generator, so the nonlinear flows can be trained based on both energy and data. I think that this is a key difference between the Boltzmann generator and the other generating models. So firstly, so if we have some data example from the equilibrium distribution of the molecular system, and of course we can simply use the maximum likelihood, right, and try to train all the parameters of the neural network. But at the same time, so if we do not have any data, but if we just have some Boltzmann distribution defined by the force field of the molecular system. So this is the most common case in computational chemistry. And in this case, we can measure the KR divergence between the true Boltzmann distribution and the distribution defined by the nonlinear flow. And it can be shown that the KR divergence can be expressed by this equation. So here, this equation, this is just an expected value on the variable z, and z is distributed according to the symbol distribution, just like the Gaussian distribution. Okay, and then we can simply do something like this one. So we only need to draw a lot of samples according to the Gaussian distribution, standard Gaussian distribution, and then we use this nonlinear flow and transfer it into some complicated distributions, and we can calculate the corresponding loss function, and then we just use the stochastic gradient descent and to optimize all the parameters. That's it. And then in fact, so we show that such an algorithm, it can be used to approximate very complicated distributions of the molecular systems without any data. So we only need some energy. We do not have any data, but we can still perform such an approximation. And another advantage is that so the Boltzmann generator or the nonlinear flow, by using the nonlinear flow, we can get asymptotically a best estimation of any observables that we are interested in. So this cannot be done by the GAN or the other generating model. So for example, if we are interested in the, we are interested in the stationary probability of the folding state of a protein system, okay, then we can define the OX to be the indicator function of the folding state, all right? And then we can draw a lot of samples by using the nonlinear flow. But please remember that we know both the density of the generated density defined by the model, and we also know the true density Boltzmann distribution defined by the true force field. Okay, then we can use, for example, important sampling to get some unbiased estimation about, or MCMC in the latent space to get some unbiased estimation about the stationary probability of the folding state. Okay. This cannot be done by, for example, GAN, right? Because for GAN, you can train the GAN very well, but you don't know what's the difference between the probability density of the output and the true density, right? This cannot be done by the GAN. And another very important advantage is that, so based on the Boltzmann generator, we can calculate the free energy difference between two conformation states. This is a really important conclusion because the free energy difference, so this quantity is very important in the biophysics, okay? And generally speaking, in the traditional method, if people want to calculate the free energy difference, then people need to design a lot of intermediate states between two states, okay? And try to calculate the free energies one by one, and then combine all of them to get the final free energy difference. But by using the Boltzmann generator, we can what we can do, we can directly compute the free energy of one state and the other. And then we simply just calculate the difference between them. That's it. So it gives us a very efficient way to calculate the free energy difference. Okay, so we apply this method to a protein system. So this is called the BBTI. So this protein system, it contains about 900 atoms, and so then you can say that it is in fact about it has a dimension of 2,700. Okay. And yes, so we train the knowledge flow based on the algorithm proposed by us. And so these configurations are the configurations generated by the neural network. Okay, and it is well known that this protein has two states. So one state is that there are something like a crystal here, and this is some open structure here. And our model can successfully generate the two standard configurations of the molecular system. And we can also calculate the free energy difference between the two states. And the accuracy can be comparable to some traditional but very time-consuming method. Okay, so this is about the sampling. And one recent progress is that we further combine the nominal flow and the traditional MC steps. So this is published in your RPS 2020.
Can I ask a question on the Boltzmann generator? Sure. Yeah. How does it scale with the dimensions? If I go from, let's say, 100 dimensions to 200 dimensions, what's the cost?
What's the cost? Sorry, what do you mean by cost here? You mean the computational cost, or?
Yeah, computational, not for the protein, but for the Boltzmann generator itself, because I understand it's more general than even a gun, and I know how gun scales, but I don't know how Boltzmann generator would scale with the number of dimensions.
Okay, so in fact, in the community of machine learning, people use it can also use this structure to generate figures. So just like a GAN. And in our examples, and I think for the system with about thousands of freedom of degree, that is okay. But for higher ones, there may be a little slow. I think the key disadvantage of the Boltzmann generator or the knowledge flow is that how to say the training procedure may be a little slower than the GAN. I think that would be the cost. I don't know if this is what you mean.
Well, I meant like if I go from, let's say I observe in GANs, if I go from 100 dimensions to 200 dimensions, like I target a distribution, let's say, the cost I pay is sort of quadratic. It's like 4 times, let's say. I double the dimensions, I pay 4 times the cost, but it's not exponential, for example. So I was wondering if the Boltzmann generator has such a property, or it explodes exponentially.
Sorry, this is really unknown. We do not do such investigation. Oh, okay. You mean, so for example, if we have double dimension, then what is the training cost, right?
That's correct. Yeah.
No, we do not do such investigation. Sorry. Yeah, but I think okay. So one thing. So at least for now, I think so. For molecular system, thousands of dimensions that can be done in some acceptable time. But for higher dimension, for example, we also try to use it to model the molecular dynamics with solvent, with explicit solvent. Then this is really the problem. It is too slow to learn such a system. Yeah, I think the knowledge flow for extremely high dimensional systems, there will be some problem. But sorry, I don't know if there are any systematic research on these directions about the cost and dimension.
For the protein, how many degrees of freedom how many degrees
so here in this system, it is about 3,000 degree of freedom.
Okay.
Okay, so one recent progress is so we call it the stochastic Knowledge flow. So we will combine the knowledge flow and the traditional MCMC steps, and we can combine them in a structure of the like a sandwich. Okay. So in fact, so we will use knowledge flow to perform the deterministic transformation, and we will use the traditional MCMC steps to perform some stochastic transformation and deterministic transformation and the stochastic transformation, the one by one. And we found that so such a structure, it can significantly improve the approximate accuracy for complicated distributions. Okay, and the key problem is that it's here because we add some MCMC steps here, then the Mackinac distribution at the output layer it is not trackable anymore. But fortunately, the whole path of the transformation, the probability is still trajectory. The path probability is still trackable, and then we can perform training based on the trackable path probability. And we can still get some Andrew-based learning and data-based learning. And yeah, this is the for example. So here we use some advantage poster to define some complicated distributions. So for example, this is a phase, right? And we assume that the black point means the density is high, and for the white area, we assume that the density is small. Okay. And then we use, so IMVP is a kind of specific nonlinear flow. And we can see that if we just use nonlinear flow itself, then the result is very fuzzy, right? It is very unclear. If we use a traditional MCMC step, because this is just a two-dimensional problem. And so yes, for small area, it can approximate the density very well, but because the convergence ratio of the Metropolis algorithm is too slow, then we cannot get a good description of the global distribution, right? If we combine both the deterministic distribution defined by the flow and the MCMC step, we can get a very good result, just like this. Okay, and we also applied it to the antipeptide system, and so here we use it to try to predict the distribution of the different dihedral angles. And the black line is the true distribution, and the red line is estimated by the stochastic Knowledge flow, and the blue line is estimated by the Boltzmann Generator. And then we will see that they have the similar shapes, but the stochastic Knowledge flow can get a better estimated result at the detailed part, at the small area. Okay.
Well, why it works so well?
Okay, so in fact, so in my opinion, I think that the knowledge flow, because it must be invertible. So that means it's the model capacity. In fact, it is somehow questionable. So that means if we try to approximate a very complicated distribution, then maybe we need a lot of layers. The number of layers may be extremely long. But for Metropolis or MCMC steps, this is in fact can capture a very good distribution, especially at some small area, right? Because the Metropolis or MCMC is somehow a universal approximator for the distributions, so in some sense. And so in fact, so such a structure, that means we can use the determinants, we use the flow to get some global description about the distribution. And then we use MCMC to modify the detailed part or the small areas. And then we combine them. So and then it can get some better result. I don't know if it can somehow answer your question.
No, I'm glad it works. I don't understand why it works so well, but that's good. It's good to work.
Yeah, because okay, so if you only use knowledge flow, so you can get some global description, but I mean the details is ignored, right? The detail is nothing. So that means, so for example, we can draw examples at this area, and if we perform some MCMC steps, MCMC it is slow. I mean, the convergence rate may be very slow, but for the small area, we can get a very good approximation about the distribution. I think that's a major reason.
How my interpretation is that looking at this is that actually it acts as a refiner of the Metropolis algorithm, because if you look at the Metropolis algorithm, it gives you but a diffusive result, and then the normalizing flow makes the features more refined. So it's not like, I would call it Metropolis plus RNVP, not RNVP plus Metropolis.
Okay. Yeah, I agree. Okay, so that is okay, and this is one ongoing research. So that means we try to also combine the macro modeling and the sampling, but not in the sense of the tram. Okay, so here I propose that another way is that, so we found that the norming flow, it can not only be used to approximate the station distribution, it can also help us to understand the kinetics or modeling the kinetics. This is different from the linear model that we considered before. So this the norming flow will give us a new way to perform the model reduction. So this is our recent work. So the structure like this one. So let's go back to the macro modeling. Okay, so we have some very high dimensional state. Okay, xt. Then we try to use a norming flow. So this is an invertible transformation, and we hope that the norming flow can decompose the xt into two parts. For example, the first several dimensions is one part, and the remaining is another part. And we hope that the two parts, one part is just a Vt, and we hope that this part is independent of the kinetics. So this is just some noise, and we hope that the other part, so the important part, the first part, is really related to the kinetics, and we can call it the reaction coordinate that we want to get. So this is Zt, okay? And further, we hope that the Zt, the reduced kinetics of Zt at the space of reaction coordinate can follow some simple law. For example, just a Brownian dynamics driven by some force field. Okay, then we can construct another model here to describe the reduced kinetics. Okay, then we can get Zt plus tau according to the kinetics. And then please remember that norming flow is invertible. Then we can combine Zt plus tau and another independent noise, and then we can get xt plus tau. Okay, so the full state at next step, and we can then combine all the steps here, and then we can get a complete distribution from xt to the xt plus tau. And again, we can also get some model reduction strategy based on this structure. And the important thing is that here we can, after training, the reduced kinetics in the space of the reaction coordinates can obey some simple law, simple dynamics. So we call it the reaction coordinate flow. And in contrast,
may I ask a simple question?
Okay.
I see that this box quantity is in fact a stochastic differential. So I was wondering, when you have that prediction Zt plus tau, is it the output of your neural network, or you have to also take in consideration of some stochastic calculus, or you just bypass the whole calculus and you can make predictions?
Okay. Several points. Firstly, so here, for this part, we only need to model the potential function v, right? And so after that, so here, in fact, I think there are some way to do that. And here we just use the simple Euler discretization, and to calculate the conditional transition, the conditional probability density of Zt plus tau for given Zt. Okay, and in applications, in fact, we do not usually perform this model. We just try to use this model to fit the kinetics of the reaction coordinate. Okay, so that means in practice, what we will do, we will So we are given the transition pair in the full state space, okay, xt and xt plus tau. And then they will be decomposed both Zt and Vt, so both Zt plus tau and Vt plus tau. And we will compute the transition density from Zt to Vt plus tau based on this model. We will also compute the transition probability from Zt plus tau to xt plus tau based on this model. Okay, so this is just the model, and we try to optimize all the parameters of this model based on the maximum likelihood. So in fact, this model will not be really simulated. I don't know if I answer your question.
Yeah, yes, to some extent, but I'll read your papers to get the exact details. But thank you, thank you.
Okay, you're welcome. In fact, this manual experience is still in preparation, and after finished, I'll give it to you. Okay, so I want to emphasize is that so the major advantage of this method over the web and the other method, for example, the past future information bottleneck proposed by Tivari, is that so firstly, we can get some interpretable low-dimensional energy landscape based on this method. I will show you later. And the second advantage is that we can easily generate the original molecular configurations of the metastable states or the transition states, because here, so it is very easy to obtain the mapping from the low-dimensional representation to the full state, to low-dimensional representation to the full state of the system, right, or the full state configuration. And so this is just to show you some one toy example, okay? So suppose that we have, for example here, suppose that we have diffusion process in a two-dimensional space, and so it is driven by two potential wells, okay? So there are potential well here and here. And then we use our method to reduce the dimension from 2 to 1. And this figure shows us the free energy along the reaction coordinate. So we can see that there are two potential wells here. After dimension reduction, we still get two potential wells, okay? And more importantly, so if we try to find the saddle point here along the reaction coordinate, we can see that it is still corresponding to the saddle point at the original system. And for this is a Mueller potential, and the result are similar. So we can see that there are three potential wells, and they can also be identified at the free energy of the one-dimensional reaction coordinate, and the saddle point is still the saddle point here. And this is a diffusion process with 7 potential wells, okay? And we use some nonlinear transformation to map it to the three-dimensional space, like a Swiss room, okay? And then we can see that our method can well unfold the data and still get 7 potential wells here. So we can see that, so from such a model, we can get some interpretable result of the, some interpretable reduced kinetics. And we also applied it to the, again, LNP-peptide. And for this one, it is well known that the conformation dynamics of LNP-peptide can be well described by two dihedral angles of phi and psi. And then we can get 6 metastable states from the landscape of the two dihedral angles. And here we also use our method to get to reaction coordinate, and we will see that the same metastable states can also be identified by these two reaction coordinates. So that means this is somehow zero choice for us. And so here we try to apply combine the reaction coordinate flow and the adaptive sampling. So wait a moment. So my battery is too low. Wait a moment. Oh, sorry. So here we try to combine this method and to propose a new adaptive sampling. So this is something like this one. So suppose that we first perform some direct MD here, and then we use RC flow to get some low-dimensional representation of the system, and we can get the free energy landscape here. The important thing is that because this is a low-dimensional representation, then it is easy for us to find the potential values and the set points by using, for example, string method. A string method can work very well in a low-dimensional system, but for high-dimensional system, it cannot work. So here, we can use string method to find the set point, and then we can, for example, perform MD simulations again, but starting from the set points. Then we can get some high-efficient adaptive sampling strategy, and then we can iteratively to perform the adaptive sampling by the 3 steps. So this is a joint work with my cooperator in the theory education again. And yes, so that is a very brief introduction about my recent works on how to apply AI techniques to solve some thermodynamic and kinetic analysis of the molecular dynamics. And I would like to thank the funds provided by Tongji University, and some of the ideas also comes from the long program of the in 2019 at UCLA, and I would like to thank my collaborations, and that's it. So thank you very much. This is a long talk, and thanks for interest. And any questions are welcome.
Okay, thank you very much, Professor Wu, for this great talk. So is there any other questions?
Maybe, Shuhui, maybe the Boltzmann generators could be useful for functional priors, or the stochastic, sorry, the stochastic and normalized flow.
Mm-hmm.
I was talking to one of my postdocs, Shuhui. Maybe he has a question on the stochastic normalizing flow.
Yes, I think normalizing flow will be more suitable for the Boltzmann generator, because in GANs we need some samples from the distribution. But in the Boltzmann generator, they only have the density. They don't have any samples from this distribution.
Yes.
So
he says he used data and energy to get.
Yes. Yeah, but the stochastic normalizing flow can also be trained by both energy and data based. Mm-hmm.
Yeah, but I can think about it, how to combine it together.
I thought you actually had the normalizing flow as an alternative.
Yes.
But the question is, I mean, what Professor Wu showed us, that you can combine that with MCMC and you get this good.
Actually, Minnan present one or two papers on this topic about before the pandemic, and
no, I know, but it was this stochastic flow or not? Stochastic normalizing
it's very similar. It's to combine the normalizing flow and HMC.
Oh,
I think I think the method Minnan presented will be more efficient than this one.
Yinlang, do you remember when you made the presentation?
That was a long time ago. So, but I needed time to pick up what I was presenting.
Okay, so this idea is, I think the original idea is proposed also in the field of computational chemistry, and I think it is published maybe 2011. So they call it NCMC, so not even something Monte Carlo. But in that paper, they don't know. So because in 2011, the people don't know the normalizing flow, and so there is no systematic way to optimize the deterministic transformation. And here, our major contribution is that, so firstly, we use normalizing flow. So we found, I think this is a very powerful tool for us. And another thing is that we found a systematic way to train all the deterministic transformations and the MCMC steps in a unified framework.
And yeah, is there any other questions?
Professor Wu, you're using this protein because it's the smallest protein, right?
You mean BBTI?
The what is it called? The peptide. Sorry, the peptide. Yeah.
You mean this one?
Yeah, the alanine dipeptide. It's the smallest.
Yeah, this is okay. This molecular system in fact contains about 10 heavy atoms. So the freedom of degree is about 30. So this is really a toy example for molecular dynamics.
Yeah. Yeah, very good talk. Thank you very much for enlightening us.
Yeah, thank you for giving me such an opportunity, and I'm very honored to give you the talk. Thank you. And if you have any interest in, so you are welcome to contact with me if you have any. Yes, you can contact me with the email here.
Yeah, we may come back to you about stochastic normalizing flow. That looks really interesting. Yeah.
Okay, that's good. That's good. Thank you very much.
Okay, thank you again, Professor Wu, for giving this great talk, and hope you have a good night in China. Yeah.
Okay.
So yeah. So let's move on to our second speaker. So our second speaker is Professor Yue Yu from Department of Mathematics in Lehigh University. So she is currently an associate professor there, and previously she was a PhD student in our Crunch group before 2014. Her research concerns topics in the areas of numerical analysis, scientific computing, and machine learning. She works on the development of novel numerical tools for models with background in science, engineering, and biomedicine, with particular interest in applying mathematical analysis knowledges in the design and analysis of mathematical models and numerical schemes. So today she's gonna give a talk with the title Nonlocal Kernel Network, a stable and resolution independent deep neural network. So let's welcome Professor Yu for her talk.
Yeah, so thank you so much. Can you guys hear me?
Yes.
Yeah, but we cannot see you. We only see your forehead. Maybe you can lower your camera.
Okay, yeah, so thank you so much, Enrique, for the nice introduction, and thank you, George, for the nice invitation. It's really an honor to present our work here. So yeah, so today this talk will be given by me and my student, and yeah, George, also your academic grandson, so Huai Qian, so who's also here. So I will give the first part, and Huai Qian will present the second part. So yeah, so basically this is a joint work with my collaborators, Meta D'Elia and Stuart Sealing at the Sandia National Lab, and Tian Gao at IBM Research. So okay, yeah. So this talk will have briefly four parts. So firstly, I'm going to cover the background and also the formulation, especially where does this idea come from. And then Huai Qian will present the details in the empirical experiments and the analysis for results, as well as the conclusion and discussions. So, okay, yeah, so firstly, what are we trying to propose? So what we are trying to work on is a novel deep neural network architecture. So basically our desired properties are the following. So firstly, we hope that it can be generalizable across different parameters, different loadings, and different spatial resolutions. So here, different parameters, you can think of like in the PD learning task, then it's generalizable to different, like say, diffusivity parameter or different Young's modulus Poisson ratio, like the material parameters. And then different loading means like if you apply different loading, so the kind of different forcing term, then it's still applicable. So that means if you already train a set of the neural network, you change the loading, then it can be directly applied for the solution prediction task. And then the third property will be kind of the main focus here is the generalizable between different spatial resolutions. So here I show two examples, which are also the main tasks we are going to discuss in this work. So what does the generalizable in spatial resolution means? So the left-hand side is a PDE learning task. So that means if my training samples are all given in maybe, for example, some coarse mesh, like for example, if on the 750 nodes, then hopefully the learning result, the neural network, can also be applied into testing samples, but with different resolutions. So for example, here, like 3,000 nodes. But however, we hope that basically the errors, the kind of the training, the testing error we get will still be in a similar scale as the training error. So on the other hand, the right-hand side is the second task, that's the image classification. So similarly, we hope that if you use the training set with one image resolution, so for example, here is 14 by 14 pixels. This is the one of the sample image from Cypher, the handwritten numbers. So if our neural network, so hopefully by training our neural network can actually do a good classification of this image. So we can tell, so the neural network can tell this is a handwritten 0. And then we hope that then we can apply the same architecture of this neural network to the testing of a different image with a different resolution. Then it can still be able to give us the correct class of this handwritten number. So of course, here the example I show is like training on coarse mesh and apply on the fine mesh. But yeah, but in the realistic, we hope that it can also do vice versa. So for example, you can do training on the fine mesh or the fine image, and then do the testing on a coarse resolution. So that is the first goal. And the second goal is we hope that it's also allow like deep neural network, deep layers. So especially for as we are going to see later in the empirical experiments, especially for the image classification tasks. So when the image gets a little bit more complicated, then usually like a relatively deeper neural network will be required. So therefore, we hope that when we try to add more and more depths into this neural network, hopefully we can get, firstly, hopefully it's at least stable. So that means the training loss wouldn't get much larger. And on the other hand, hopefully it will be even, because if you add more depths, then the training is more expensive. So of course, hopefully it will also get a better accuracy.
Can I ask a quick question here?
Yeah, please.
This is Yanjong.
Yeah, hi.
Hi.
Yeah, nice to meet
so
you.
for image classification, the training input dimension and testing input dimension is different. So I'm not sure how architecture is testing high dimensional input than training.
Yeah, that's a perfect question. I'm going to show in the examples.
Okay.
Yeah. That's a perfect question. Yeah, that's actually one of the aims of this design here. So yeah, so basically, if you change the resolution, then you don't need to. I would say the input size, then you don't really need to change the architecture. You don't really. I would say you don't really need to change the parameter. Yeah. So yeah, that's a very nice question. So then the third property, which is kind of like one way to see why this design is stable, is we can see that this design will be has a connection with the nonlocal parabolic equation. So for the nonlocal parabolic equation, we know that, well, as far as it's coercive and bounded, then the nonlocal calculus can tell us it's guaranteed to be stable. So yeah, so that offers some kind of the theoretical kind of the guarantee for our design neural network in the deep layer limit. And then so then in this talk, I'm going to, moreover, we hope that this deep neural network architecture is applicable to different tasks. So for example, here, I'm going to show the PDE learning task and the image classification task. We can see that we don't need to change much into the architecture to handle, these two types of the tasks. So, okay, yeah. So before I jump into more details, so firstly, I'm going to give some background about what is the PDE learning task and what is kind of a general architecture of the neural network will look like in the PDE learning task. So in the PDE learning task, we assume that there is a given domain, which we call D here, and on this domain there is a kind of a differential operator, which we call L here. This differential operator might depend on some parameter function. So this parameter function you can think of, if this is a heterogeneous problem, then this parameter function is basically maybe the kind of the diffusivity function, or like the kind of the Young's modulus, which is a function on this domain. So then what we are looking for is, given a forcing term F and given such a parameter function B, we are looking for the solution U. So that is our PD learning task. So so then how do we generate the samples, including the training and the testing samples? That is as follows. So assume that this PD task, we are given a bunch of the measurements on different nodes. So here the nodes, the total number of nodes, I call it M here. So each training sample is given by the measurements of the parameter B on those nodes, a measurement of the loading on those nodes, and the solution on those nodes. So then our input can be our input, as we are going to see later, it can be the forcing term, it can be the parameter. So taking the forcing term, for example, the input of the neural network will be the forcing term, and then we firstly transfer that into the features. So this feature we call H can be of like a higher order, like a higher dimensional vector. So then basically the loading in each discretization point is transferred into the feature in this discretization point, and then there will be interactions in the neural network, like between different nodes, and then finally go through like L layers of neural networks. Then we kind of transfer the feature back into our output. So that will be the solution we are looking for at those discretization points. So that is a kind of a typical design for the neural network for the PD learning task. So then what might be the possible pitfall when we try to generalize that into different resolutions? That will mainly be the interaction parts. So that means like when it goes from layer 1 to layer 2, you can see that basically there are interactions between the nodes. It can be seen as basically the edge value or in a graph. So the edge value, when we change the resolution, so for example, if now my testing, the sample has like say maybe like say m prime numbers of nodes, then possibly it will require different values of those different weights for this interaction between the nodes. So that will create a possible pitfall to make the neural network not so generalizable to different resolutions. So yeah, so then here is our desired property in this design. Of course, we want to avoid this pitfall. So we hope that our neural network we can design is generalizable. So here the generalizable means, well, it's firstly generalizable to different resolution. So that means, well, if we already train a neural network, and then if we give an input which is of a different resolution, so of course that will be a longer vector, then we can still make the neural network kind of applicable. So that means our prediction, our output will still be with a similar accuracy as before. So then another generalizable we mean is, we hope it's also generalizable to different parameters and the different loading. So that means if you apply a different B and a different F, hopefully that's still generalizable. So here, therefore here we emphasize that the training set, we take the M numbers of the nodes, and the testing sets, we have M prime numbers of the nodes. Here the M prime can be drastically different from M. And also here the training set, the loading and the parameter, the B and the F, could be also different from the testing set, the parameter B and F. And the second desired property we are looking for is the stability. So we hope that if you try to, as I said before, if you try to increase the number of layers, like if you increase the number of L here, then hopefully we can have still have a stable performance, meaning that the training loss is not going to kind of increase drastically. And moreover, we hope that, especially in the applications that require deep neural network, we hope that the training error can be even improved.
I have a question.
Please.
So M prime can be much bigger than M, or you restrict the values of M prime?
We didn't restrict that here. Of course, if the M prime is like say much closer, that's possible. You will lose some of the accuracy. So yeah, but however, in our test, I think we at least test when the M prime is like, we test when the M prime is like 16 times smaller or larger than M. I think that still works. So that means if it's a 2D task, then basically you kind of refine the resolution by 2 times, or sorry, by 4 times on each dimension.
Okay, thank you.
Yeah, so I think that you can see more details in the empirical results. So in some of the tasks, we do observe that when you try to train on a fine mesh, and then you try to apply that on a coarser mesh, then you lose some accuracy. But I think that's probably not the problem of the neural network. It's more related with that if you are if you try to test on a coarser mesh, then basically your feature, you are going to lose some of the important features. So, okay. So yeah, so here is the second task, that is the image classification. So for the image classification, the task can be roughly described as follows. If we are given an image which can be seen as like say a matrix with a bunch of the pixels with n numbers of the pixel values. So we hope to find a label for that. So especially for the classification task, assuming that there is like L numbers of possible labels, then we hope that given this image, which is a vector in the dimension M, then we can find its label, which is a vector of dimension L. So for the image classification task, before I talk about the detailed architecture, first thing I want to define what does the cross resolution means. So because the image can be kind of seen as a kind of a discrete matrix, discrete vector. So here, to see what does that mean by the cross resolution, we kind of see the image as a continuous function instead. So that means it's similar to the idea of like say a finite volume or like a mesh-free method in our PDE solvers. So we associate each image as a continuous function, which we call A here, and the value of A is given in the middle of each pixel. So then our training sample will be as the following. So our training sample is the value of the pixel for each image and the corresponding label of it. So now we can investigate the architecture too. So the architecture we can see is very similar to the one in the PD learning task, but except that when we try to transfer the feature out into the solution, into the output, we apply a softmax layer to kind of to transfer the labels to transfer the features into labels in dimension L. So yeah, so then similarly for the image classification task, we also look for the generalizability. So that means, well, if you try to train with maybe like say an image of a kind of a coarser image, then the classification accuracy will still be very similar in a finer image or vice versa. And then we also look for the stability. For the image classification task, especially for the complicated examples such as cipher, then it's important to use more layers. So a deep architecture will be required to have a good accuracy. So therefore, we hope that our neural network will still be stable in such a deeper limit. So Okay, yeah, so before I jump into more details, let me try to kind of give a very brief and maybe of course incomplete summary of some state-of-the-art methods, especially in the PDE learning task. So here I want to emphasize so this kind of the list of methods is not complete. So the first type of the method can be seen. Basically the current SOTA methods in PDE learning can be roughly contains 3 types of the groups. So the first type can be seen, the first approach trying to parameterize the solution operator as a deep neural network or especially deep convolutional neural network between finite Euclidean spaces. So for example, here we have like say n numbers of the nodes of the measurements on the domain, and then it's kind of like the learns an operator between these n numbers of the measurements, for example, for the loading or for the parameter to the solution, which is also like a vector of size n. So such an approach is, at least by its definition, not mesh independent. So therefore, if you want to apply the learned neural network to different resolutions and the different discretizations, it cannot be directly applied. So you need to maybe add modifications to make sure that it's generalizable to different resolution. And the second type of the approach is basically trying to, it's more mesh independent because the solution is defined on the physical domain. Basically, it's trying to directly parameterize the solution as a neural network. So from the domain D into the kind of the solution value. So one of the so by design, it's not designed to be applied to a different loading because in some of them, because in this type of the method, we assume that we already know what is the PDE. So what is the PDE governing equation? So therefore, in this case, it depends on the parameters. And therefore, if you want to apply that to a different parameter, say B or different loading, then very likely you have to train the neural network again. So the third type is mainly what we are going to call the graph kernel network here, which was first developed in the last year. What they try to do is they try to build an approximation of the solution operator by construct a parametric map from the loading term to the solution directly. So, but however, as we are going to see soon, they are currently restricted to shallow networks. So, okay, so then maybe let's start from the third type of the neural network architecture I've been talking about. So let's start from an elliptic equation for its simplicity. So in the elliptic equation, basically there is elliptic operator L and the solution U, the operator applying on the solution U will be equal to the loading F. So in this type of the problem, the solution can be represented by the Green's function. So here, if we denote the Green's function as G, which depends on the parameter B here, then the solution can be written as an integral of the Green's function, multiplying the loading and take an integral of that on the whole domain. So in the graph kernel network, the authors propose to, instead of parameterize for the solution, they try to parameterize for the Green's function. So if you try to parameterize the Green's function, you can use a neural network to approximate the Green's function G here. So that is what they introduce as the neural network K here. This is usually a very shallow neural network. So this neural network, the input is the values at points X, Y, and also the parameters of that. And then the parameter, the parameter for this neural network is denoted as V, that is the trainable parameter, that the weights and the bias for this neural network. So this K can be think of as a non-local kernel function. So then here I'm going, and also in the later of this talk, I'm going to mark all the trainable parameters as in blue. So here, so therefore, this is the final architecture for the original graph kernel network. So the else layer network update is given by the following. So it's given by the integral, which is something like similar as the integral of the Green's function, which is represented by a graph neural network, and which is represented by a neural network, and then the a matrix R here, so which a weight matrix R here, so which is also trainable, and also the kind of a bias vector, so that is the C here, which is also trainable. So this type of the graph kernel network, why it tends to be generalizable to different resolutions. Let's try to see the reason why. So, and the key for the generalizable to different resolution. So basically as we have explained before, the possible pitfall for the generalization to different resolution, it actually lies in the interaction between different nodes in the features across layer. So the key here is they are trying to control these interactions by this graph, by this non-local kernel K. So this non-local kernel K is actually parameterized by this neural network. So so that means this non-local kernel K, it can be seen as basically a function in the physical space. So therefore, it doesn't depend on the resolution. But in the real implementation, how do they implement that to make sure this is still true? So basically, they employ a message passing graph network architecture. So so basically, what they are doing here is for each of the node in this neural network, that the integral is implemented by a summation of the edge values and the node values. So that means, for example, for each of the point X, assuming that it kind of can be interacting with its neighbor of size R, which is in a sphere of the radius R, and then in that case, it will be the edge value, which is characterized by this K multiplying with the feature value in the last layer, and then take a Riemann sum of it. So one of the key here is if you try to apply that to a different resolution, then this radius R should be chosen in the physical space. It shouldn't change. So for example, here I show that, well, if the training is like say on the m equal 11, but the testing is on m prime equal 23rd, so that means you add more nodes into there, then the R should be kept the same. But however, the graph, of course, will become denser because of it. So that means when this R is chosen in the physical space, then that is one of the key features to make sure that the neural network K is a continuous and mesh independent kernel in the physical space, because that approximates the Green's function in the physical space. So so now maybe let's try to see the performance of this graph kernel network in one of the application. So one of the basic applications. So let's consider a 1D Poisson's equation. So in this case, the graph, the Green's function, the explicit Green's function can be written out. So which is plotted as above here. So in this case, if there is only one layer in the graph kernel network, then the neural network K will be directly analog to the Green's function. It will provide a direct approximation of the Green's function. So therefore, when the graph kernel network has only one layer, you can see as shown in the plot here, it provides a very good approximation of the ground truth Green's function. But however, the pitfall happens when we apply more layers in the graph kernel network. So when we apply more layers, then the training loss is increased from 10 to the -2 to like order of 1. So if you try to take a look at the Green's function it's trying to approximate, we can see that the training picks up nothing. So it's kind of the training kind of has a very large error in the Green's function. The Green's function is almost like showing a constant. So why is this happening? Let's try to take a look into what's happening in each layer. So what we are trying to do here is we try to take a linearized GKN network. So that is also employed in the original paper for this task. So that means the activation function, sigma here, is taken as the identity operator. And then we try to see, well, what is the amplification factor from the layer L to the layer L plus 1. So this amplification factor is actually a matrix. So we will try to see that, well, what is the eigenvalue of this matrix? So when the eigenvalue of this matrix are all below, the magnitude of that, when it's all below 1, then that means basically the information from the layer L to the layer L plus 1 is it's actually passing in a stable way. But if it's above 1, then you can think of when you increase the number of L, then it's going to blow up. So that is what we see. So here we try to plot out the layer, basically the amplification factor, the eigenvalue of this amplification matrix when we employ like 1 layer GKN, 2 layer GKN, up to 8 layer GKN. So this is the amplification eigenvalue for each layer. So here for the first, when there's only 1 layer, that is when we see a very good approximation of the Green's function, we can see that we have like quite stable eigenvalue. It's below 1. The magnitude is below 1. When we have 2 layers, then it's still below 1. But however, you can see when we increase to 4 layers, then the largest eigenvalue is already larger than 1. And if we take 8 layers also, it's larger than 1. So that's the reason why that it becomes unstable, because the amplification factor will be above 1. So now, yeah, so then now how can we fix that? How can we make this GKN like also applicable to the deep neural network? So here are 2 remedy ideas. So the first idea is actually we found that from a kind of an image classification task, a computer vision task. So that was, so it's basically it was originally so it was actually starts from the so-called non-local neural network proposed in the IEEE paper in 2018. So in this paper, the authors proposed the following non-local neural network architecture. So basically, from the L's layer to the L plus 1 layer, they tried to use a kernel. So this is a given kernel K, and then to try to integrate the information of the nodes, and then they apply a weight matrix weight matrix W. So this W is changed with different layers, and also it's the trainable parameter. And then they claim that by this type of the non-local neural network architecture, they can have a better accuracy than in the computer vision tasks than the traditional convolutional neural networks. So, but however, in this type of the architecture, we can see that it can be seen as a discrete version and also a fixed kernel version as the GKN. But however, they met the same pitfall as GKN. So when they increase, it was found that when they increase the number of layers from 1 to 4, then you can see the training loss is actually going to increase. So instead of decreasing. And if you try to zoom in, try to see the eigenvalues of this W for each layer, when there is 4 blocks, we can see that the eigenvalue becomes large. So the eigenvalue is as large as 20. So that's the reason why that the training loss gets increased, because the neural network becomes unstable. So therefore, also in 2018, Chang and Yunzhe has proposed the following idea in their NIPS paper. So they try to borrow the idea from the non-local diffusion equation. So the idea is quite simple. So instead of, like, say, simply integrate over the neighborhood, they propose to kind of subtract also the node value in the current node. So therefore, this operator becomes an analog to the non-local diffusion operator. And then they are still trying to train, they are still using a fixed kernel, and they are still trying to train for the weight matrix W here. So then when they try to still use 4 blocks and try to plot out, try to see how does the eigenvalue is at, you can see the eigenvalue becomes much more stable. So yeah, so that is the first remedy idea we borrow from. And the second remedy idea we borrow from is from a derived in the also from the computer vision task. So it was proposed by Haber and Lothoto also in 2018 in the AAAI paper. So what they try to propose is they consider a convolutional neural network architecture, but however, they write that into a ResNet formulation. So that means each layer, so when we transfer from the layer L to the layer L+1, there is a kind of a neural network, which, so there is basically, it's parameterized, the residue here, and the residue depends on layer L, and also it's parameterized by parameter V here. So the V is the trainable part. So in their idea, they develop the so-called the shallow to deep technique. So in this technique, they try to rewrite this ResNet architecture as an ODE system. So basically, you can see that it can be seen as the derivative of H is equal to R tilde. So then by doing that, they see when you take the number of layers to infinite, that is equivalent to you take the delta T here to 0. So then they assume that this ResNet architecture will actually converge, take the limit to this ODE system. So with that aspect of view, then they should share the same set of the parameter V here. So therefore, what they propose is as follows. When they try to train for 4 layers, then they simply use the parameter V trained from the 2 layer as the initial value for the parameter for 4 layer. And then you can see that if they don't use this technique, then the training loss will be as in the blue line. So when you try to transfer from 2 layer to 4 layer, it's going to kind of get increase again. But however, if you use this technique, then you can see that the start training loss is much smaller. So, okay, so now here is our proposed formulation. So our proposed formulation, we try to use the ideas from the 3 works we have been just talking about. So basically, we propose the architecture as follows. So in each layer, we try to write that as a ResNet architecture. So from layer L to layer L+1, then it's the first part is given by an architecture which is analog to the non-local diffusion operator. And then moreover, we also have a parameter R, which is actually only applied on the current node. So later we are going to talk about why this R is also important. That can be seen as basically as a reaction coefficient in the parabolic equation. And then also, again, a bias vector C. So then this architecture is slightly different from the original GKN as follows. So although we still have the K to provide the kernel for the integral operator as in GKN, but besides that, we also have a parameter L provided for the advection term. But however, this advection term is only applied to the current node. So for the current node from this layer to the next layer. So therefore, the R part is not going to create a pitfall in the generalization to different resolutions.
May I? So when you talk about the advection, you're talking about like something similar to a drift term in the diffusion in the diffusion equation, right?
Yeah, right. Yeah. So this is like an advection diffusion equation. Yeah, exactly.
So okay, so the R term is the drift.
Yeah, right. Exactly.
Okay.
Exactly. Yeah.
And Okay, and the kernel is not temporally varying. It can be spatially varying, but it cannot be temporally varying, because I do not see a parameter t in the kernel.
Yeah, that's a very good question. So in the I would say in our vanilla version, it's not temporarily varying. Although we can also make it temporarily varying, but however, if you make it temporarily varying, then it might be more difficult to do the shallow to deep technique. And the other reason why we didn't make it temporarily varying is because we want to reduce the number of parameters, because the training is already very expensive. And that's also the case for the original GKN. But I think Huaichen will show you guys that in one of the image classification tasks for the sci-fi, we also try to make it temporarily varying. If it's temporarily varying, then you can get better accuracy.
Okay, okay. So okay, and that argument b of x, b of y, what is that argument? Is it like is it in this example, is it spatially varying?
You mean bx and the by?
What are those arguments? You have x, y, bx, by, and v.
Oh, yeah. X and y are basically the value on basically the node on the physical domain. And the bx and the by are the corresponding parameter. What I would say, basically the corresponding parameters of that. You can think of that as the diffusion parameter, or you can think of that like maybe like say the stiffness on these given nodes in a heterogeneous material. So here, the k can be seen as an analog to the Green's function. So the Green's function, it depends on x, depends on y, and also depends on your parameter. So that's why it depends on these 4 parameters here.
Okay, so this is something to do with the physics. So I don't study materials, so I don't know about that. But I understand that this kernel is spatially varying.
Yeah, right. This kernel is this kernel is spatially varying. Yeah, you can say it this way exactly. So it's spatially varying, but it still is defined on the physical domain.
Van, let her finish, because we have another person, two people presenting.
Okay. Yeah. Okay. Yeah. Thank you, George. Yeah. So okay. So now what is the detailed formulation? The detailed formulation is given by the following. So firstly, in the first layer, we try to transfer the input. So in the PD learning task, that is basically that is the position and also the parameter. In the image classification task, that will be the image pixel values into the feature space. So that the feature LH, it will be our first layer. And then we try to use this this NKN architecture for L numbers of layers. For each layer, we are using the architecture we proposed before. But however, here in the real implementation, we also use the message passing networks. So that means basically for the integral is actually implemented as a Riemann sum, and this Riemann sum is taken in for radius r. And then finally, after we get the last layer, we transfer the last layer back into our solution. So in the PDE task, that will be the solution U, and in the image classification task, that will be the label. So here I also highlight all the trainable parameters. So in this particular case, so in the vanilla version I'm presenting here, we assume that this V, W, and the C are the same for different layers. So for all the L layers, they share the same parameter. But however, later we have also tried to make it like can be varied for different layers, and we see better accuracy. But of course, the training is more expensive. So now let's try to see where did we borrow ideas from, like the non-local neural network, the shallow to deep technique, and also to the GKN. So firstly, we the idea of GKN is applying for the interaction between different nodes, the feature between different nodes. It's also implemented, as I said before, as a message passing neural network, which can be seen as a Riemann sum for the integral in the physical domain. So that is the key to make it generalizable between different spatial resolutions. So the second type, so then the second part is for the generalizable between so to the stability to the deeper layer is implemented as following. So basically we can see that we borrow the idea from the non-local diffusion operator. So therefore, basically the edge, the interaction, we also subtract with the value from the current node. That's the idea from Qiang and Yunzhe. And then on the other hand, this architecture, if you try to subtract the edge xt to the left-hand side and divide by delta t, you can see that it's actually of a ResNet architecture. It's parallel to a non-local differential equation. So that is the key to make the shallow to deep technique applicable. That will help us help the training in the deep layer limit. So yeah, so then, like I said before, if you try to subtract the edge to the left-hand side and divide the both-hand sides by a delta t, then as the delta t goes to 0, that means when this neural network go to very deep layer limit, then it's parallel, it's corresponding to the following parabolic non-local equation. So you can see the first term is actually a non-local diffusion operator, and the second term is actually the kind of the activation operator. So it becomes a diffusion advection diffusion. Sorry, that's an advection term. So it becomes an advection diffusion non-local equation. So now we can use the tool in our non-local calculus to analyze that. So this analyze can tell us what will happen in the very, very deep layer limit. So actually we can show that as far as the eigenvalue for these two parts, so basically the non-local diffusion part as well as the advection part, as far as they are both bounded and positive, then we can show that this non-local parabolic problem is well posed and stable. So that means as far as the eigenvalues are all positive, then we can guarantee that it's, and also bounded, then we can guarantee that it's going to be stable. So now let's try to see if if our proposed network really kind of stabilize the original architecture comparing with GKN. So remember, this is the example that GKN fails when we try to use more layers. So here the kind of the bottom right plot, I show the results from our NKN. We can see that the training loss is increased a little bit comparing with one layer, because of course in this example, if we have one layer, then the kind of the kernel we learn is analog to the Green's function. So that's the most accurate case. But however, you can see the training loss doesn't increase much comparing with the O1 loss we have observed in GKN. Here we have the training loss is like 10 to the -3, and it still gives a good approximation of the Green's function. So now to take a deeper look, let's also try to see what about the eigenvalues. So but here I want to emphasize the eigenvalue we are analyzing here is actually not the eigenvalue of the diffusion and the activate and the advection terms is actually as before. That is the eigenvalue that for the amplification factor from layer L to layer L+1. So that means similar as before, as far as it's all below 1, then the magnitude is all below 1, then we can guarantee it's stable. So yeah, so remember before in the GKN, we see that when it goes to 4 layers and the 8 layers, then this eigenvalue is above 1. So make it unstable. But here we can see even for 4 layer and 8 layer, that's still quite stable, all below 1. Okay, yeah, so I think I'm going to pass the floor to Huaiqian to explain the empirical experiment settings and the results.
Thank you. Can you share my slides?
So do you want to share your screen, Huaiqian? Or
Screen.
yeah, so maybe that will make it easier for you to turn the slides.
Okay.
Thank you.
So we have two different learning tasks for the empirical experimental results, two for PDE learning and two for image classification. The first task is the Wendy-Poisson's equation. So the basic setting is, well, the domain is a one-dimensional interval from 0 to 1, and the training sample Fn and the Un satisfy this relation, and they are generated by the discrete Fourier transform. So in this case, the domain of integration is the entire domain, which means the R we mentioned before is 1. So each particle is connected with all the other particles within the domain. And here, the dimension of K and R are listed here. Because in this case, the parameter B is a constant. It's 1 over the entire domain. So the kernel network K only takes in two input, is X and Y. And here the feature of H is said to be 1 because this task is simple enough. One dimensional already produces very good results. And we compare the training and the test result with GKN. As you can see here, as the number of layers increase, the GKN, we observe the instability in GKN both for train and test. And in our NKN, we observe a much more stable results. And also as the number of layer increases, the test accuracy is improved. So besides that, we also do a ablation study in this test that we want to see that what's the impact of this R term. So we try to set R to be 0 for this NKN test, and then we compare the training and test results. As you can see here in this table, when we set R to be 0, so the training and test accuracy is not as good as the original NKN formula, but it's still better than the GKN. So another perspective, another angle to see this is compare the eigenvalue. So as we remember, we showed before for the NKN formulation, for both 4 layers and 8 layers here, the amplification factor is less than 1. The largest one is around 0.6 and 0.8. But when we set R to be 0, we can see the largest eigenvalue is already above 1, which means that the absence of the R term compromises stability property of the NKN formula. So, and the next example is the 2D Darcy's equation. This one is more complicated. Here, the displacement and the loading satisfy this condition. And the domain is a 2D square. And here the feature of H is 64. We have 64 dimensions. And because it is a 2D problem and the feature is much larger than the first one. So because of the computational limit, we can only integrate over a neighborhood of each particle here. And we can't afford it to integrate over the entire domain. And in this case, K is a 3-layer neural network with the dimension listed here. The input dimension 6 is consistent with before. We have X and a Y and a BX and a BY. So R is also a 3-layer feed-forward network with the dimension listed here. Here we show that the effectiveness of the shallow to deep approach. As you can see, the blue line is the one this one comes from the random initialization, and the black line is the one that's we use a shallow to deep technique. So basically, the idea is when we first train a 1-layer results and they use that as an initial value to initialize a 2-layer neural network. And also we use the 2-layer results to initialize the 4-layer neural network. And we use that over and over again until the last layer. So as you can see, if we don't use a shallow to deep approach, we use the random initialization, the training loss, especially for the high number of layers, is very hard to decrease. And even when it's reached the plateau, it's not as good as the shallow layers. But when we use the shallow to deep approach, we can see a consistent improvement as we increase the number of layers. So by using this shallow to deep neural network, we calculate the training on 2 different resolutions. One is SS16, the other is SS31, and we compare with GKN. As you can see, for all those number of layers, our method consistently, I would say, for the shallow network, GKN does a pretty good job. And for a deeper and deeper neural network, our NKN can outperform the GKN, both in SS16 and SS31. And also we test the cross-resolution validation. We test the generalization property on the different resolutions. So here we try to train on one resolution and test on the other. You can see we try train on a coarser mesh, one SS16, and test on a fine mesh 31. And also we try to train on a fine mesh S31 and test on a coarse mesh S prime equals 16. For both those cross resolution tests, our NKN can beat the GKN, especially in high number of layers. So next, I will move to the image classification tasks. So we have 2 different image classification tasks. The first one, we use the MINIST dataset. And the second one, we use the Cypher10 dataset. So MINIST dataset is handwritten numbers from 0 to 9. And the Cypher10 dataset consists of 10 different tasks, 10 different classes. So here, there are some settings in common. In both of those tests, we set the dimension of H is 16. And also the domain of integration is a neighborhood instead of the entire domain. Here, K is a 3-layer neural network with a dimension listed here. R is also a 3-layer network with a dimension here. So for the MINIST dataset, we call the original dataset that consists of 28 times 28 pixel images the fine image, and we call the 14 times 14 images coarse images. And these coarse images are generated by the fine image via bilinear interpolation. And this is the structure of this MINIST task. So here, here AX and A, here AI is the AI is the input, and the CI is the label. So first, we connect the input to our NKN layer. And also, basically everything is the same with the PD learning. Only difference is at the end of it, we connect the output to a softmax layer, and we calculate the label from the softmax layer. So here we compare the results with a very basic CNN and also the non-local neural network. We call it NNN here. And we use a different integration radius R equals 2 and 3 and 4. So as you can see, so here we present results as a train on fine image and then validate also on fine and coarse, and also train on coarse image and then validate on fine and coarse. So basically here, the first column is the training and validation on the same resolution. Here, the second column, the fourth column is also the similar. It's also the same resolution. The second and the third column are the cross resolution results. So as you can see from the table, the CNN does a very good job on the same resolution training and validation. That's because it's designed for those type of tasks. And the NKN and NN does a better job in the cross resolution results. Especially our NKN can have a cross resolution accuracy. It's like 5%, which is still better than NN, which is around 10%. And also next, we compare the NKN with different radius R. Here, as you can see, except for the radius R equals 2, the other the other radius equal 4 and 3, the cross-resolution accuracy for radius equal 3 and 4 are consistently around 5%. That's possible because when R is too small, like 2, only a very small number of grid points are inside the kernel. So it kind of makes sense that it cannot guarantee a very good cross-resolution accuracy. And we can see from here, when we increase the radius from 3 to 4, we don't see a very significant improvement. That's possibly because this MNIST data set is too simple, and R equals 3 is already sufficient enough to produce a very good result. So next learning task is the Cypher10 data set. So here we call the fine images. So here the original images are 32 by 32 pixels. Here we call the fine image, here we refer to the fine image as a 64 by 64 image, and the coarse image is the 16 by 16 pixels image. So both are generated from the original image by linear interpolation. So instead of directly connect the NKN or NKN to the input, so here we use a structure called a pre-ResNet, and we insert a number of blocks of NNN and NKN to the pre-ResNet. And here we allowed K and R to be temporal variant to better improve the accuracy. And also here we compare the compares accuracy on the original resolution set, and also on the fine images and the cross resolution results on fine images and the coarse images. So as you can see, when we use R equals 4 blocks 4, our method can have an error like 7.08, which is much better than the baseline, also the best case in and for this cross-resolution test, because as you can see from the previous example, CNN really does a better job in this cross-resolution test. And here our NNN and NKN are inserted into a bunch of different ResNet blocks, which contains a lot of CNNs. So it's hard to compare, to show the cross-resolution results. In the baseline, what we use is we basically use a different resolution of images, and you can see this is not very good. So in our NNN and NKN comparison here, what we do is we use the idea of multi-scale CNN that in different resolutions, we use a prolongation matrix and a restriction matrix to modify the weights of the CNN kernel, and then which is equivalent to we will resize the image before and after the NNN and NKN blocks. So for example, here for the fine test, which is equivalent to we upsample the image before the NNN and NKN blocks, and after all those blocks, we downsample it again. So do it in this way that the CNNs in the pre-ResNet in the pre-ResNet structure won't influence the entire cross-resolution validation. We can just compare the performance of NKN and NNN. As you can see, our method can outperform the NNN in the cross-resolution validations. So to summarize, NKN treat the feature space continuously by means of integral operators acting on the node domain. So as such, their accuracy is independent of the discretization size. And by identifying layers with the time instance, NKNs can be interpreted as discrete non-local time-dependent diffusion reaction equations, which is guaranteed to be stable. And the stability of NKNs allows for accelerated learning techniques for deep networks, such as the shallow to deep technique, for which the optimal parameters of shallow networks are used as initial guess of deeper and deeper networks. And the last part, in both image classification and the PD learning tasks, NKNs are stable and generalizable and outperform baseline methods. So here is a list of properties of GKNs, NNNs, and NKNs. As you can see, our formula has advantages in can do both PD learning and image classification, and has advantage in stability, and also its a resolution independence. Okay, so last part, I would like to thank our collaborators, Marta Delia and Stewart Sealing from Sandian National Lab, and Tian Gao from IBM. And I would like to thank NSF for the funding support. Thank you.
Great. Thank you, Huaiqian and Yue, for your wonderful talk. So is there any questions from the audience?
Yeah, can I ask a question?
Sure, go ahead.
Yeah, in the conclusion that the first one that it said that accuracy is independent of the discretization, can that be made as a general statement, or if the problem has very high variance in the domain, then I think like my question is, if you use a low resolution to train, that it might not behave well when you go for the higher resolution, since the domain might have high variance in a very small interval.
So you see, if the domain has a very high variance in small interval.
Yeah, like in the solution space, if the solution is like too much varying in a small domain, then if you are training it in a small resolution, when you go to higher resolution, that the accuracy might decrease, right?
Yes, that's a very good question. I think the thing is you have to choose the integration domain carefully. So as you can see, this is kind of similar as what we see here in the image classification. When radius is 2, the cross resolution results is not very good. That's because the integration domain is too small. It doesn't contain enough information. I think for your question, I think it's kind of similar. We have to choose that the integration domain is large enough, so contains all the information from the domain. Like say, if this domain is high variant, we need to have a large enough integration domain for this NKN to see those different informations within the domain. Otherwise, I think it won't have a very good performance.
Thank you.
Hi, I have a question. Thank you very much for the talk, but I kind of missed that. If you train on fine grained and you validate on coarse grain, how would you convert the dimension of the input?
That's also a very good question. So for those inputs, for example, if we start from 28 by 28, so those H really doesn't depend on the input, the dimension of the pixels here. Because we are learning the K and R. Let me go to the previous slides. So from our formulation, we are learning K and R. So this is basically the setup. So K and R, basically we're learning the relation between each particles. We're not learning from so this K and R doesn't depend on the size of the image. We're only learning a relation between each particles. Let me put it this way. So the only thing, for example, for the image classification task, you can see here, the K has a 3 feed-forward network with a dimension 4, 32, 32, and 256. So here the 4 inputs are the coordinates of X and Y. So because of 2 dimensions, so we have 2 inputs. When we change the resolution, the only thing changes the input. So the coordination of these 2 points, 2 nodes are changed. So our lambda parameter can still be used on this situation.
Okay, thank you.
Lulu, do you have any questions?
Yes. Could we go back to the table of the area of the PDEs for the
this one?
Yes. For example, not cross. Do we have a same resolution? Yeah, for example here. So how do you sample the B and the F?
Oh.
How do we generate the set?
So here we use the data provided by the GKN work. So here B is a two-valued function with a random geometry, and the ratio between two value is 4. And F is, I believe, is 0 over the domain.
Okay, I see.
Mm-hmm.
Okay, and then for the super resolution, so what if I directly have a pre-processing layer? For example, if I network trained on low resolution, then for high resolution, I got to do a downsampling, or if I have the low resolution, I try to go high resolution, I use interpolation like a GP. So what's the error if I just do some this kind of simple pre-processing?
Oh, you mean like just do the resizing?
Yeah, for example, for CNN, let's say the CNN is trained on 16 by 16 pixels. Then when I try to predict for the 32 by 32 pixels, I simply do a downsampling to the 32 by 32. Then I use my previous CNN network.
Yeah, that's a very good question. So for CNN, we test on different data sets. Our result is if you just simply do the downsampling and the upsampling, so I believe the accuracy is around like 40% or 50%.
Why? I think the accuracy, at least the accuracy of the low resolution, right? For example, in the previous CNN table, for example, if the CNN that is trained on coarse resolution is accuracy 2%, then if I have a high resolution, if I do downsampling to the coarse, I at least have 2%, right? Because I can do 2% on the coarse.
Oh, sorry, I misunderstood your question. All right. Yes, we didn't show the results here. I think if we simply do the downsampling, if I remember correctly, the accuracy is about, if we simply do the downsampling, the accuracy, I think is about 15 to 20% in this minister case. Sorry, the error is about 15 to 20% in this minister case. So here, what we show the result here is we didn't do any downsampling or upsampling. We just use the different resolution image as the input.
Yes, it helped me to understand why. Because if the CNN can have 2% accuracy on the coarse image, then for good image, I downsampling to the coarse, I should have at least 2%, right? Why go back? Why become 20% or 15%?
Because I think one of the reasons is when you go into downsampling image, you lost some information. So, so the image you got from downsampling.
But the validation error, for example, the validation error on the coarse image, so it's already 2%. So which means in your validation or testing, we are also try to predict the coarse image label from the coarse image.
Yes. Yeah, so here we, this 1.84 is we trained on coarse image and validate also on coarse image.
Yes, yeah. Okay, thank you.
Yeah. So I don't have the exact number here, but I believe if we do, if we only do simply just do down sampling, it's not as good as this 2%. Yeah.
All right. If there's no more questions, so please join me in welcome our.
Minglang.
All right.
May I?
Yeah, one last question. Please go
yes. This is a follow-up from our discussion. So I understand you have a different neural network for learning the drift term and the kernel for the diffusion, or you have the same neural network.
So sorry, say it again. So you're asking, do we have the? So in the last part, in the last task, we allow this K and R to be different for each block, means it's temporal variant. For the previous tasks, we set up that the K and R are the same between all these blocks.
Go back a couple of slides, please.
This one.
Couple of slides more. Back to non-local kernel. A little bit more. Yes, next slide. In here, exactly. So you have two neural networks. One is learning the drift term, and the other is learning the kernel. And you have the same loss function driving both the neural network. Is it correct?
So our loss function. So our loss function is the L2 norm between the for example here is L2 norm between the U produced by this neural network and the data. So we have a loss function just minimizing the solution error.
That is correct. I agree with you, but the output but the objective is to learn the kernel and the drift term, right?
Mm-hmm. Yeah.
So you have two different neural networks. For one gives you the kernel and the other gives you the drift term, or you have the same neural network giving you both the quantities.
Yes.
Which one?
So in this model, we train those two neural networks at the same time. So here K is basically the non-local diffusion kernel, and here R is the advection term. And I don't know which one. Sorry, I don't quite follow your question. Can you say it again?
Are you there?
Maybe I'm sorry to interrupt, but it's already 2.5 hours. So maybe you guys can discuss this shortly offline. But again, thank you so much for your wonderful talk.
Thank you.
I'll send you the recording in a following email, right?
Thank you.
Yeah. All right, that's the end of this week's seminar. Everybody have a good weekend. Bye.
Bye. Thank you.